I understand. Right. No, but no. It's only the screen here. Okay. So let's try to define. Let's try to define these things. So when you say push forward, the question is push forward of what? Okay. Is it right? So I do not. So there is one con of a set. Okay, but so what does it give? Does it give you a set again or right? But that is right. Okay, so let's then consider just a mapping from one topological space to another topological space. So what does it mean to say push forward? So maybe we can say push forward. But why will you call that a push forward? But why? But so it is just that's just then that's just a word. So that's not. But then that's not how. That's not what it usually is defined in mathematical. Okay. Uh, no, because push forward usually has not to do with subject. Right. Push forward has not to do with subject. Let me just give you. No, it's okay. That's a good point. I mean, injectivity might sometimes be needed. Might uh, but that might be some different context. I don't know. It might yes that it's a different idea. I mean, it could both be. Yes. Okay, so let me just think of an example of push forward. Then I can tell you. Yes, we can take that. It's fine. That's fine. So they can have different topologies, right? It doesn't have to be the same. Okay, so let me take two manifolds. So yeah, let's take two manifolds to give you an example of push forward. Let's take two manifolds. You can just think of Mn and as Rn if you like. And now I'm just taking a continuous function or no, sorry, a differentiable function. Differentiable function. So f differential. Then there is something called df, which is the derivative of f. Right. So the abstract definition is that it goes from the tangent bundle, but we may not need this to the tangent bundle. But if you, but we can first come to the pointwise definition that df at every x goes from the tangent space at x to tangent space at x. And basically now you see that this f, which was a map in some world, like between two manifolds, now it is inducing a map between some sort of two different worlds, which is this tangent space and this tangent space at the respective at the same point. Okay, I'm sorry, so this is something wrong. This is fx x, and you see, so it's inducing a map, and it's inducing a map in the same direction. Okay, so this right, and this dxf we can say is like a push forward induced by f on the tangent spaces. Okay, we can let's try to just define it explicitly. then it will be more clear, I hope. But how? Can you tell me how? Uh, yeah, I do not know. Yes, it. Mhm. Mhm. By, yeah, those. What are those? Uh-huh. Mhm. Right. Okay. Yes. So I could, we can take, yes. Yeah, it could be something very interesting. But I obviously I will not know because of I don't know the context. Yes. Right. Yes. Yes. It could be. I mean, why not? Because uh, yes, because like for example, if you have let M and N be again just be manifold topological spaces, then if you take the collection of all singular I chains on M, this just in the spirit of what you're saying, uh, singular I chains of on M to singular I chains on N, and just to define this, this is the singular I chains are uh, uh, no, so I should be careful. Yeah. So this is just the free abelian group, or this is like a Z model, or in general R model, generated by these functions, which are from delta I, which is I simplex, to M. And here you have the free abelian group, or in general an R model, generated by, again, I chains on M. And you can see that this will induce this now. This is actually more straightforward, right? But you will need two things, like if you have F, sorry, I'm using the same F, so maybe you should use G. Or maybe G is not a good enough. Yeah, but like this F and this G are not in the same, they don't have the same status in some sense, right? This G is of a different nature. So I would not call it G, I would call it some phi. I mean, it has a different nature, that's a different kind of objects. Anyways, so I feel that choosing good notations is a superpower because it feels like that's the only thing I'm doing when I'm doing mathematics. Okay, yes, yeah, that is true. That is true. But also like yes, yes, that's right. But that's of course the one aspect. But what I have in mind is that good notations can actually evoke the correct idea. Okay, the correct notation, yeah, like it could tell you what to do. So in that sense, like I think I had one friend whom I just was very good mathematician, and like he would do the mathematics, very great mathematics, but he would do them very casually, as if he's doing nothing. But when it will come time to pick a notation, he will ask everyone, "What do you think should be the correct notation?" So that's why I think it's really very important. But anyways, we are just doing some basic stuff. Anyways, so the point is that this phi equals to this, right? And so you have a map on the generators, and by the universal property of free modules, you have a map on the modules. on the from the generators to the from basis to vector map from the vector spaces. And so this is an example of a push forward. And these things are examples of these things are like contravariant. These things are contravariant functions. Sorry, covariant functions, which you can see the precise definition. Yeah, but let's just come back to the topic and just try to define this derivative map. Yeah? I think that that way we can do some see some mathematics also how this map is defined. So this thing. So do you have a definition of the tangent space for a manifold? Tangent bundle or tangent space. So do you have a definition for a general manifold? It's actually a very deep thing to the definition for manifolds. Uh, yeah. Hmm. That's yes, but then it's just a set. But how is it a manifold? Okay, so we don't need that. Um, yeah, you are okay. So we have x. So we have a point x, and x is in U, and U is in M, and U is let's say diffeomorphic to. So you have a yes, it's diffeomorphic to Rn. Okay, 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 okay. Then so how do you define Pxm? Yeah, so to make it actually mathematical is not so trivial. Yeah, and yeah, because it took years to come up with the definition. It evolved over time. So I don't think it's completely yeah trivial. So yeah, so mhm. Yes. Mhm. Mhm. Uh, mhm. But what is a normal at the point and I don't know that. What does it mean to say normal? Okay. Okay. Yes, okay. So it's diffeomorphic. It's a diffeomorphic. Okay. Right. Okay. I mean, yes, I mean, I don't because, but the problem is that, yeah, the normal, but no, I mean, normal doesn't exist, right? You're taking a ball, doesn't exist. Yeah, that's just, yes, 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 yes. You can just think, sure. Yes, yeah, unless we try, I mean, I should also just think because I don't know. Yes, yes, yes. It should come more or less independently, more or less. Yes. Yeah. Right. We have you might assume, if you like, you might assume that this is sitting inside some large Rn, if but may not be useful. You can assume that it has a topology, so it has curves is at passing through X. That's a fine from the interval. Yeah, they are in M, they are in capital M, and hence they are in R capital N if you need to use that. Or maybe I will just suggest that maybe you don't need, this might actually confuse me for the moment. Might not, because I don't even feel how it will help me if I assume. But it has, but you can have curves passing through the point X in the manifold. I think so, yes. Yes, yes. Because those are completely, that is an intrinsic concept. Tangents, tangent is not intrinsic, it needs a diffeomorphism. Curve is intrinsic. Yes, it's yes, you can take collection of curves. Uh, all the curves should be included in the tangent space. Yeah, just think about Rn case. All the curves are included in the tangent space because directional derivatives you can. So from there, right. Yes, actually that's yes, yes. Is almost TPX. Yes, just that when you go forward with this definition, you will see that this definition, you will automatically realize that this definition is slightly incomplete. Okay, slightly mathematically not so good. So what we do is we quotient it. Okay? We quotient this by an equivalence relation. Okay, we quotient this by an equivalence relation, or why do we have to do that? Because you would want your tangent space to be a finite dimensional vector space. Right. So you should have to quotient this, but uh, right. Yeah. And what you will have to quotient with, maybe let me not say that now. You think about it. Okay. Is that thing? Yeah. So basically you have one of the correct definitions. There are other definitions also. But since you have one definition, it's fine. The other definition is basically the dual of C1M X. But it's called the derivations on C1M. But let's not get it because it becomes a discussion. No, not singular chains. Yeah. So so I'll just tell you. So this is basically the family of germs of function at point X, right? Which is basically the collection of all continuous functions, right, on M, but continuous in a neighborhood of X. Okay, and this is continuous and smooth derivative, and the derivative is continuous. So this is that collection, and then you want linear functionals. You want linear functionals from You want linear functionals on. Yes, yes, exactly. I mean, we have to just linearize. Yeah, and axiomatically put the Leibniz rule somewhere. That's the fact because that may not just because yeah, yeah. So that is something should happen. So dot dot dot. So you can put that definition. So and then you can show that both the definitions are one and the same. Okay? And then that yes, yes, that's absolutely the point. You should think about the tangent space as an infinitesimal neighborhood around X, but it's some sort of flattened neighborhood, some sort of flat, because that's the only thing we know in some sense. I mean, otherwise, what else can we do, right? If we are asked to compute something, we just done nothing. I mean, just think about it, right? What we cannot do much. You can, yes. So Lee's book would be good. Lee, since you have read, gone through one of his books, so you can see Lee's smooth manifolds, or even you can look at his topological. I will suggest you look at his smooth manifolds if you want to learn differentiation. Hmm. Hmm. But it's wonderful. Just read it. Yeah, Espumarism. Yes, yes, yes. In the yes, and it is one of the standard books. It cannot be bad. I've never read it, but it will not be bad. And I can tell you, it's going to be a good book. And Kumarasan is of course one. You can read that. And the exact book doesn't matter. These things you have to create. Like you created a small definition here. So in this way, you have to do most of. Um, but yeah, it's, yes, it's fine. Yeah, right. So yeah, that is thing. And then how do you define this finally? Let's take your definition of curves. So how would you define this thing? Now it's very simple, right? Just take the curve. Yes, and just push the curve, right, gamma, and just you just push gamma by f. You get a curve there. So you see, from this definition, it just get you get a. I mean, because you get a definition here, and like there can be no other definition. Given this definition of tangent space, you cannot come up with some other definition. This is the only possibility in some reasonable sense. And then tangent bundle is another story. It's, in some way, it's another story because you have to put a topology on. Oh, in what way? Right. Right. Hmm. That is true. Yeah, it's true. But also, yes, but also, I mean, it's called right. Yeah, and bundle, of course, is going to do what? Yeah, yeah. All the, but then you must notice that that involves all the points also. It's not for a fixed point. Yeah, TXM is for a fixed point, and that is the bundle of all the points. So that's one of the reasons. Yeah. Yes, yes, and no, yeah, and then you have to find a reasonable way to bundle. Right, and that's actually some slightly involved. I don't know. I think so. It might be. Yeah, yeah, but it turns out that usually they are equivalent. uh, tangent space. No, tangent space. Tangent space. No, tangent space. Yes. Oh, it's actually it's also a fiber in some sense, but for us it's a tangent space for now. Yes. Right. But it's only locally. Globally, it's not Euclidean. Locally, it is Euclidean, but globally, it is not. So when you have to do a global bundle, because you have to globalize the definition, and that is where it's very intriguing. Yes, yes. It could, yeah, it could not be. It's very. That's because it depends on your definition. But obviously, in standard, there is one accepted definition, and it has different ways to define. There are different equivalent ways to define. Yes, yes. But there could be other definitions also, which could be useful for other things. But that's true for anything. So it's generic. You could if you want, you can study these things. Tangent boundaries. It's really a very interesting object because, for example, if you take a circle, then you know that I mean you can intuitively feel that the tangent bundle is a cylinder, right? So S1 is in R2, right? But then when you're taking the tangent bundle or tangent space at every point, you get lines at every point, and then the tangent bundle is yeah, right. And so you can intuitively feel that it should be the cylinder, right? So, no, because you have a circle, and at every point you have the tangent space vertically like this. Well, yes, and an infinite annulus is a cylinder, right? So in that sense, but yes, but it is infinite. But uh, no, no. But I'm not saying in that way. I'm saying that if you have an annulus like this, then if you just turn it like this, then it becomes a cylinder. That sense, yeah. But then if you have just a circle, then at every point the tangent space is just a line. Circle is one dimensional. So you have lines at every point on the boundary of the circle, and that is cylinder. So in that sense, cylinder, yeah. So you would imagine that it should be a cylinder, and topologically it turns out to be a cylinder. But but that's a very special case. So in that, what is a cylinder? A cylinder is S1 cross R. Right. So it turns out for S1, it's S1 cross R. But for S2, the tangent bundle is not S2 cross R. It is some twisted or no. It's but we're talking about infinite. Yes, but that's a minor thing. Yes, that is infinite. Yes, because it's space. That's why we say tangent space. Right. But the interesting thing is that for the tangent bundle of the sphere, okay, right, which is R2 at every point of S2. Yes. So then why is it not S2 cross R2? Yes, but that is not. I mean, but yes, that's right. I yes, but I understand the behavior. but then you see, I mean, that's not a reason to say that it cannot be S2 cross R2. Because S2 cross R2 lives in some four-dimensional space. So there maybe they don't intersect. Yeah, yeah. But yeah, I mean, no, at every point it is R2. At every point it is R2, right? Because at every point you just have the plane. But overall it is not S2 cross R2. But for it's just this abstract space, TS. I don't know more than that. It could have some interesting meaning, but that's a good question. What is it? We should try to find out. I don't know. It's not S2 cross R2, that I know, and even to prove that it's a bit tricky. That requires the hairy ball theorem, if you may have heard from algebra topology. So that can be applied to prove that it's not S2 cross R2. So things get very interesting. Yeah. So that's it. But then I think that for some spheres, like maybe S7 or something, or maybe S3, I think it is trivial. Right, yeah. Okay. I was just saying that for S3, I think it is S3 cross R, the tangent. It is trivial. It's a strange thing. No, 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 oh, no. Only for three spheres it is this like this. A trivial like 10 this cross with a corresponding arcade, and for others it is not. Yes, yes, and it has to do with the right. It has to do with the fact that S2 does not have a Lie group structure. Yeah. But if you want, we can try to prove this using Harry Potter. I don't. I don't know. I don't know. This is 2 cross R2. I don't know how to visualize. That's the problem. That is why we need mathematics. No, how is it easy? It is in some four dimensions. At a point, TS2 at a point. Yes, yes. I understand. Yeah, right. No, no. But the problem is this, that you have planes at every point, but that is not how the topology will make it look like. That is our human intuition that makes us imagine that it should be like that. But the topology of the tangent bundle says that it does not necessarily have to look like. We have to put some topology. So if you want, we can try. We can just discuss both. No, it's not Euclidean. It's not Euclidean. It is not. And so first you have to define what is a tangent bundle. How is it a manifold? What are the charts on it? So then you can. No, but how can you consider? Then it will not be. I mean, okay. Then you are saying that I don't know. So then you are saying maybe that you define it as just disjoint union of Tx. Yeah, but this may not be a useful definition. Yes, because yeah, I tend to say why it is not useful. I don't know that, but usually we don't. Yes. Yeah, but as I say, I don't have the reason for it. That is a problem. But we are just I don't know, but yes, you can say, but like I don't know, you can still get a map from here to this. That you can do. right? Because if you have map from each txm, yes, yes, because there's nothing interesting to say in some way. Yes, 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 I agree. Yes, but let me try to think why we don't define it like this. Hmm. Well, yes. So one of the things is that yes, the tangent bundle is equal to this as a set. Okay? But the topology on the tangent bundle is not the disjoint union topology. It's not the disjoint sum or whatever topology. And why that is, you see, it will not take into account certain things. Hmm. Because you can always make this definition. Yes, yes, right. So, yes, yes. So one of the yeah, yeah. The exam was fine. Uh, yes, the exam was fine. I could not do three questions. Uh, I mean, so actually both the papers were subjective, and the first paper I could not do two questions, and the second paper I could not do one question. Yes, yes, yes. Still cannot do them. I still cannot do two of them. One of them, it's easy. I just missed it. But I can tell you the questions at the end. But let me tell you why this is not a good. So because you see, yes, yeah, that's fine. Yeah, so that's fine. Now, so yeah, so now you see the problem with this definition is that if you have two manifolds, let's say S1 and R1, R, okay? If you define the tangent bundle like this, then the then the tangent bundle of S1 will be same as tangent bundle of R. Right, because S1 and R1 there is a set theoretic bijection, right? And that will give you a isomorphism here if you take this definition. So so you can take this definition. We don't want it, right? Because you want a yes, because you want to make definitions which have nuances, which can help you to distinguish between your original objects. Because so the original objects. Because see, one thing is clear that if two spaces are diffeomorphic, then their tangent bundles should also be diffeomorphic, right? That is certain because you want your definition to be mathematical, and mathematical definition means that it should not depend on a particular reincarnation of the object. It should just depend on the abstract features of the object, right? So, if two manifolds are diffeomorphic, their tangent bundles should be diffeomorphic. But you want a definition which is like this. If two manifolds are not diffeomorphic, then their tangent bundles are not diffeomorphic. Right. You hope for this kind of definition. Okay. Even though that hope is not met, you will find examples of non-diffeomorphic manifolds whose tangent bundles are diffeomorphic. But still, more and more, if you can differentiate, it is better. But this definition is on the other side of that thing. It doesn't differentiate even between S1 and R, compact and non-compact. Right. So certainly we will not take this. This could be one because I mean because Because it's not a mathematical question, right? Why is not a definition is not a mathematical question. Because math, yes, right, yes, it's certainly a very important question, I would say, but it can, yes, 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 that is what we want to know, right? Because so that we can also do some mathematics, hopefully. Huh. Very, yes, yes, unfortunately, that is what has happened to at least me. But we want to change that. Yeah, yeah. Huh. Okay. Mhm. Mhm. Okay. Yes. Which is not bad. Yes. Mm. Oh, okay. That's a good point. Yes. I think maybe that's why we are discussing this. Mm. Yes, yes. Yeah, we are just, just having our own experience through that thing is not bad. Yes, I suppose that's a big thing because that's what I mean. See, school teachers, what they do is not a waste because otherwise, who will carry it on to the next generation? Yes, that's important. Yeah, yeah. But at the same time, the urge to create a new piece of mathematics is also very real and at a balance. Hmm. Hmm. Or maybe when we do that, we become mathematicians. Yeah, certainly, and through that steps, certainly it's an important step, or maybe a necessary step. Okay, so no, but this is a way of, yeah, this is a way of thinking or expressing something. It has its own importance. Yes. But yes, but one should be able to do. One should. I mean, if one tries really, if one has the desire, they can do all. Somewhere we are sort of not sure about what we want to do. So that has its own place, and that happiness maybe is supposed to be a fuel to move forward, but also not being able to see the truth in those other three questions or two questions, three questions is certainly a disappointment. Yes, yes, yes. Because practically speaking, I need to do very well because so they have this bias in the interview about the age and so on. I mean, it's not a bad bias. It's probably they are perfectly right in their place. But I'm not the time to look at that. The important thing for me is to do very well because because I need to do better because I'm older. So practically, practically speaking, yes, yeah. Yes, that's maybe the case. Yes, but also so like the questions which I could do, I already knew how to do them. So from before, more or less. So yeah, again, it feels like I'm just putting life into it, but not creating. Yeah. No, no, somewhere I'm also happy. I mean, if I was very sad, I would probably not be sitting. Okay, let's. Yeah, no, I understand. Yes, a certain, yeah, certain balance. Yes, yeah, I'm also happy. It would have been worse if I could not do four questions. Like, that would have been, so I should be happy about it. Yes, yeah, okay. Yeah, certainly. That would have been very bad. So this is fine. Well, I think so. Can we, yeah, so the last day, some questions which were there, do you want to resolve them? Or yeah, or I had asked some questions to try. Yeah, if you have tried them, okay. So then you can just try that. Yes. So then, I mean, yeah, yes, yes. That question is yeah, the topology one. So, yes, yes. There, um, all the spheres in scaling to area now. I think I get what you mean, but can you make it mathematical? Okay. That's fine. That's okay. Yeah. So you do. No, no, no. That's all right. So you are saying that equivalence classes, the representatives can be picked from sphere from S2. Yes, exactly, exactly, absolutely, absolutely. Okay. Mhm. There is no map there, but okay, it's a yeah. Okay, right. Then it's a reflexivity is reflected. Okay. Oh, okay. Yeah. Sure. I it's not x1, x2. There is no x3. Mm-hmm. 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 Scaling, right? Right. Yes. Yeah. Right. Correct. Yes. Right. Yes. Yes. So those are the observations. Yes. That's true. Mhm. 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 That's true. Yes. 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 That's right. So that means your lines are your points. The lines in R3 are points of R2. Yes. Right. Yes, it's a single point. Yes. It's a real line and an R2 on the right side. That's a point. Yes, that's correct. Yes. So you are saying that you have R2 to S2. Okay. So this is the thing you were actually saying. You can call it anything. That's fine. Unit map. What is this map? Yes, stereographic projection. No, because you can prove after you do the topology and so on, what is the topology and so on, you can prove that that topologically, this is the same thing as this. So it cannot be S2. This is not S2. I mean, that also needs a proof actually. Because why that needs a proof? Because S1 quotient by X identified with minus X, diametrically opposite points, is actually S1. It's actually S1. Yeah, that's the thing. A circle. Circle. It doesn't work for it. It doesn't. Yes, but uh, yes, the inside points are not included. This is S2. Right. Yes. But yeah, here it is S1 again, but here it is not S2. Yes. But then again, you can again take this as a thing to think about why this is not S1, S2. Because that's your question basically, right? Why is RP2 not the same? Why this P2 is not S2? So how about proving it? So you put the topology and then you prove that these are not the same. And well, you can prove it if you can use fundamental group. You can say that this you can prove that this is a non-orientable manifold. It's orientable. You can, yeah. Yeah, they will all get resolved once you put the topology. So then you will know everything that there is to know. Yeah, you can do by many ways. You can do by many ways. And another thing, mhm, yep. Oh, I think there is some connection problem. Hello. Mm-hmm. Hello. Yes, I think your connection is unstable. Yes, I can hear you, but again I've lost you. No, 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 it's breaking. So no. Yes, now I think I can hear you. S- Yes, yes, now I can hear you clearly. No. Yes, that's fine. So, I mean, all I was saying is that you should now try to prove that RP2 and S2 are not homomorphic. So, you should do that. Yes, I think no, this is fine. Just try to just do it. And you can use Monkeras. Yeah. Yes, I mean, the topology on RP2 you can just find in Monkeras if you cannot do it yourself. But that's fine. And the other thing which I was saying, the last thing, is that you should also just try to make this thing also mathematical. What does it mean to say compactification? Uh, no, no, but I can hear you. Okay, that's fine. Yes, now it's fine. Yes, yes, yes. Now it's perfect. I can see you. Yes. So basically, yes. Okay, then it's Absolutely. Yeah. Yes. 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 Right. Yes. 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 So then that's fine. That's I mean, those are uh, P2. Yeah. So I mean, yeah, but P2 is a S2. Yeah, P2 is S2. Yes, I mean that's what you told me. The P2 is S2. So then, well, there is no shoot. Then there is no problem, right? I mean that you ask him. I don't. So, yeah. So maybe there is some. Maybe we can look at his paper next time. Yeah. Yeah. Okay. Well, those are. Yeah, but those are not. Yeah, but that's but then that's a very small thing. It should not bother us. I mean, that's mathematician. Uh, no. So no, no. I mean, okay. No. Don't do that. T2 is S1 cross S1. Yeah, that's up to them. That's but yeah, that's yeah. People do that. I suppose. And it could actually cause confusion, like in this case. So, anyways, yeah. So, anyways, I mean, let's call it a day. Okay. So, yeah. So you have the work, and then meet on Tuesday. Mhm. Right. Yes. And yes, and then the previous day there were some questions, right? Why RP2 is there's no surjective math and so on. So you just do them. Just try them. Yeah. So hey, this is yeah. So what else should you read? Mm. Yeah, you can read many things, but yeah, you should just read the proof of the Jordan-Schoenfeld theorem. That is one thing. So you should try to understand that because right now I feel that that is important. So you should try to understand that. So yeah, that's it. Yeah. So these are the things. I mean, you should just try them. Okay. So yeah. Okay. Yes. But usually when I fix the meeting, I try to not cancel it because then it creates a lot of confusion for everyone. Like some people have, yeah, it's not a good thing to cancel unless it's very necessary. Because cancel, yes, we actually had two courses. Yes, we had one differential geometry one and we had differential geometry two. Yeah, and we are taught by very good differential geometer, Debashish Goswami. I don't know. He's a Bhatnagar awardee, so he has done some good work. But mostly his work is in. Sorry, say that again. ISI has multiple. True. Yes. 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 Yeah, yeah, Nina. Yeah. Algebra geometry. Yes, yes. A fine algebra. Uh, some awards, many awards. Yes, yes, the Zari's cancellation problem. Yes. But she works in a fine algebra, which is a certain kind of tradition, very traditional algebraic geometry. So now the world has changed. I mean, if you talk about talk about what is happening now, or like now people have moved on to very more other things. Fine. But I suppose um, many things. I mean, so there is derived algebraic geometry, theory of motifs, and all the things. Yes. Yeah, there is yes. So there's, yeah, exactly. So K theory is one direction, and derived algebraic geometry. So I would say these are the two because the world has moved on. I mean, fine algebra geometry still has enough juice to produce paper. Yeah, to produce papers. But I would not want to work in commutative algebra or a fine algebra. Those are things of the past. In I mean, you are still getting papers out of them, but they are not grand. I mean, your ideas will not shine across different fields. They are very hopefully okay. Right. Okay. I don't even know what it is. I do know that there is some, yeah, but it's hmm, right, right. Hmm, not a member. Yeah. Yes. Right. Right. Yes.